till now we've been doing propositional logic, and now we're moving to a somewhat more complicated version of logic called predicate logic. So as I hope you remember, a proposition is a sentence that's either true or false. So for example, Kermit the Frog is green. That's a sentence that's true. 2 plus 2 equals 4, another sentence that is true. 8 is prime, well, that's a proposition, it's a sentence that is false. Now we're going to move on to predicate logic. And, the formal definition of a predicate is that it describes a property of the subject or subjects of a sentence. And so we say if P is a predicate that describes a property of X, then we write P of X. That's nice and formal. Let me show you what I mean. So for example, let G be the is green predicate, and let B be the has a banner ID predicate, and let X be Kermit the Frog, right? So if we take all of those, if we take all of these as our kind of definitions, then if I say G of X, now I'm saying Kermit the Frog is green, right? I'm making a statement about Kermit. Or I could say not B of X, in other words, Kermit the Frog does not have a banner ID. Here's another example. Let's set F to mean the sums to 4 predicate. In other words, these things add up to 4. And let X be 3, Y be 1, and Z be 2. And F is actually going to take two, I'll call it 2 parameters, right? 2 subjects. So f of xy would mean that 3 and 1 sums to 4, right? The sum of 3 and 1 is 4. It's not the case that 1 and 2 sum to 4, or 1 and 2 do not sum to 4, right? Or what's f of zz? Well, z was 2, right? So 2 and 2 sums to 4. Now, honestly, that doesn't really seem much different from the propositional logic that we've been doing. But let's talk about what happens when we get into larger collections of items. And to do that, we need to start talking about a domain, right? And not domain as in domain and range, but domain as in what is our universe that we've used. Maybe we've used the term universe in when we were talking about sets, right? So, for example, if I set my domain to be Rowan students, right? And leave B of X as has a banner ID, I could make a statement that says every single X in our domain has a banner ID, right? For all X in our domain, B of X, all Rowan students have a banner ID because I limited my domain to banner students, so everything in my domain has a banner ID. Now, of course, if I change my domain and say, oh, now my domain is American citizens, right? But I leave my predicate alone. B of X means that X has a banner ID. Well, now I could make a statement that says something like, it's not the case that for all X in our domain, B of X, right? Because not all American citizens have a banner ID. If I leave my domain as American citizens, I could make more statements using this predicate B. For example, I could say, you know what, there's at least one X in our domain such that B of X. So there is at least one American citizen who has a banner ID, right? So even though all of the X's, all the elements of our domain, B of X is not true, there's at least one of them for which B of X is indeed true. So you can see we've got sort of more complex concepts that we're doing with predicate logic than we had with propositional logic. So let's go back to our old domain of Rowan students, and we'll still have that predicate B. We could also say there exists at least one X in our domain such that B of X, right? There's at least one Rowan student who has a banner ID. And that's true. Of course, you and I happen to know that all Rowan students have banner IDs, and so that first example that we used was perfectly valid, but so is this, right? It is definitely the case that there's at least one Rowan student who has a banner ID. There's a lot of Rowan students who have banner IDs. So as with much of this course, we end up taking shortcuts in terms of our notation. And we're going to use this funky upside down A, which, if you go to a party and you want to talk about it, you could talk about the universal quantifier. But in fact, most people just translate it as for all. So if you see an upside down A, you have to think for all, right? So if we go back to that example where we were talking about our domain was Rowan students and B of X meant X has a banner ID, if we write this statement right here, for all X B of X, that says all Rowan students have banner IDs. Right? Similarly, if we do a different example, let me cross out this example, and we say, oh, you know what, our domain is actually American citizens, we could say this statement, right? And look at my parentheses here. Let me see if I can make this a little bit bigger. Okay. So what have I got here? I have got a not outside of this statement. So this statement is saying for all X in my domain, right, it is the case that X has a banner ID, except outside I've got my not, so that means that, that means that our statement is it's not the case that all American citizens have banner IDs, right? It is not the case that for all X, B of X in our domain. And I don't suppose you'll be terribly surprised to find out that there's not one but two of these nice shortcut symbols. This kind of upside down backwards E, mirror image E maybe, is called, the fancy name is the existential quantifier. But again, it's just a fancy label for a lazy shortcut. We're going to use that backwards E to represent the phrase there exists. So if we look at this first example, where my domain is Rowan students, this backwards E of X, B of X means there is some value X in my domain for which X has a banner ID, right? So specifically, there is some X in my domain where my domain is Rowan students, so there exists a Rowan student that has a banner ID, right? And this there exists means at least one, right? There could be 10,000 of them, or there could be one. But if you have the backwards E, that means there exists, the existential quantifier. And again, if we look at this other example here, and my domain is now American citizens, I can actually make the same statement, right? There is at least one element of my domain of American citizens for which that element, that person, in fact, has a banner ID. So let's talk about how to translate some English sentences into predicate logic. Okay, so let's suppose that my domain is all people. Right? So here's my domain, all people, and let H be the is human predicate. And I want to say everyone in my domain is human. Right? Well, how do I say that? I say all things in my domain are human, right? It's a nice big way to write it in English. Using predicate logic, we just write for all X, H of X. Everything is human. Okay, here's another example. Same domain, we still have the domain of people. We're going to have B this time represent the predicate has brown hair. So I want to say there exists at least one person with brown hair. Well, I said there exists, didn't I? At least one person has brown hair. There exists some X. You know, I don't have to use X. I could say exists a Z. Let's be exciting. Okay? There exists a Z such that B of Z. Right? This Z here, this X here, we'll talk more about this later, but it's like a local variable in a method, right? It whatever we use here and here, as long as they're the same, they're kind of coupled. So let's let B be the has brown hair predicate. And now I want to say there's more than one person has brown hair. And this gets a little bit trickier. In fact, I sort of need to give you another predicate for this. Let's say let's make a new predicate called N, which is the not the same predicate, which will take two parameters. So if I want to say more than one person has brown hair, what I have to say is there's two people, there's at least two people with brown hair, right? So I have to say something like there exists an X and there exists a Y, right? So there's an X and a Y such that X has brown hair and Y has brown hair. And furthermore, I didn't give myself enough room. So X has brown hair, Y has brown hair, and furthermore, X and Y are not the same person, right? And this is a little bit more complicated, right? Because now I'm using two of these for there exists, right? Which is a little bit different. But you can see, by the way, I parenthesize these, right? There's parentheses, the biggest parentheses in here is around these guys, that all of these predicates are inside of the parentheses, and they're kind of governed by this. So there exists both an X and a Y such that X has brown hair and Y has brown hair, and this is very important, X is not the same as Y, they don't equal. Okay, here's another example. We're going to let G be the has green hair predicate, very exciting, in our domain of people, and we're going to say no one has green hair. So how do we say that? No one has green hair means there's not even one of them, right? And in fact, we could write this two ways. The first way we could write it is we could write kind of the opposite of there exists one, right? So there does not, it is not the case that there exists, maybe we'll go for Y, exists a Y such that G of Y, right? So that's one way to write it, is there does not exist anybody in our domain which has green hair. Another way we could write this, which is putting across the same idea, it's the same exact concept, but said a little bit different, is we could say everybody doesn't have green hair, right? So we could say something, I'll do this in red instead. For all X, it is the case that not G of X, right? So no matter what X you take in my domain, all of them do not have green hair. And when I look at these two equivalent statements, they sort of remind me of De Morgan's. It's not exactly the same here. But to me, you know, if I have a there does not outside of this exist, that's actually the same as for all there isn't pushed in. Okay, so we're still dealing with the people domain, but now we have a predicate with two, I'm going to call them parameters. And if I want to say everybody has a parent, right? What do I have to say? Everybody has a parent. And these translations get hard, and the first time you see them, they're particularly challenging, but as you kind of see me do some and you read the book and look at some examples, I think this will get easier. But so everybody has a parent. Well, we've got to talk about two people here, right? We're talking about everyone, right? So we know we have something about for all X, right? So all people, well, everybody has, and it doesn't say has one or more parents, but you know, I guess we're going to say everybody has a parent. So we won't go for the exactly one right now. Everybody has a parent. So for all X, there is somebody, right? So for all people, there exists a person such that, let's see, we want X is the parent of Y. So I guess parent, I did this the wrong way around, but that's okay. All right. So this says every person in the world, there exists somebody where that somebody is that person's parent. Now, it's possible, it's not really true, but it's possible to say that everyone has exactly one parent. We could also say everyone has exactly two parents, but that gets a little bit tricky. If we could say everyone has exactly one parent, what do we have to say? We have to kind of say this piece that we already have, right? Everybody has a parent. And then we want to say there's only one. So, one way we could do this is we could say, all right, for all x, there exists a y such that y is x's parent. And it's also the case, and I'm going to wrap around here, that for all x, if y is x's parent and z is x's parent, then they better be the same person, right? Let me shrink this a little bit more so I can fit it. Why is this not shrinking? So let's see what we've got here. We've got everybody has a parent, right? Everybody has at least one parent. And everybody, if y is their parent and z is their parent, well, I want to say that means that y is the same as z, right? So let's see. So that implies that, and I guess we could have a, let's add another predicate. Let's have EQ of x and y mean that x equals y, right? So if there's two people, y and z, who are both the parents of x, that implies that actually there's not two people, that y and z are equal. And now let's just make sure we've got our parentheses right. Let me make a little bit more room here. There we go. So let's see, we've got this piece here. For all x, there's some y such that y is x's parent. And for all x, if y is x's parent and z is x's parent, that implies that y and z are equal. Okay, let's try this one. This one is not everyone is a parent, right? So what we have to say is either there is somebody who's not a parent, right? Or it's not the case that everyone is a parent, right? So what we have to do is we have to say, let's try it's not the case that everyone is a parent. So it is not the case that for all, maybe I'll start with z because I haven't used z much. It's not the case that everybody has somebody who they're a parent of. So it's not the case that everybody, for all z, there is somebody, there exists, I don't know. Why don't we make it make it an x. So it's not the case that all people have somebody, and now I just have to say who they're the parent of. So where z is the parent of x, right? So what did I say here? I said it's not the case that all people z have somebody x who they're parents of, who they are a parent of, right? That means that z is not a parent, right? Or I could say there are some people who are not parents of anybody, right? So I could also say there exists somebody, and maybe, oh, what the heck, I'm going to use really weird letters here just to make a point. There is somebody called A, such that for all other people B, A is not B's parent. So let's put a not there. It's not the case that A is the parent of B. All right. So that's another way to do this. And you can see, I hope, that these are two ways of saying the very same thing. Okay, here's a statement that says some people are parents, right? Let's take this a little bit. Let's take the definition of some as what do you want to do? We could do some as there's at least one person, or we could do some as there are multiple people. I think some tends to make me think multiple people. So why don't we add an equal of x and y predicate, which means x is the same as y, right? So some people are parents. That means there exists at least two people who have somebody, each of whom have somebody who's their child, right? So there exists an x and there exists a y such that x is the parent of somebody and y is the parent of somebody. So I guess we need the child of x and the child of y. Maybe we'll call them q, all right? Such that parent of, let's see, so x is the parent of c, and y is the parent of q, and x and y are not the same. So it's not the case that x equals y. So again, if we look at this, there are 4 people here, right? Possibly in this group. And I've said x is the parent of c, y is the parent of q, and the only, this is anywhere between 2 and 4 people, right? Because the only thing I've told you is for sure x doesn't equal y, right? I told you that down here. So this statement says there's somebody x who's the parent of c, there's somebody y who's the parent of q, and I guarantee you x and y are not equal. It may be that x is the same as q, or y is the same as c, or x and c and q are all the same people. That's possible, but I told you for sure x and y are not equal. Okay, here's another one. Let p of xy be x is the parent of y, predicate again. No one is their own parent, right? So there is nobody who is their own parent. This is actually an easy one, right? There does not exist an x such that x is their own parent. That was a nice, easy one. And of course, we can flip that into a for all as well if we want, right? It is the case that for all x, it is not, x is not x's parent, right? So no matter what x you pick in my domain, it's not the case that x is x's parent. So again, these two are actually equivalent statements. They mean the same thing in English, even though they look a little bit different. Okay? There is no one person who is everybody's parent, right? So what am I trying to say here? Let's see. There does not exist a person y so that for all people x, y is x's parent, right? There's no one person who is the parent to everybody else. Now, sometimes we don't want to really specify the domain, and so we can just sort of specify the domain by the predicates that we use. So for example, if we want to say not all birds can fly, we could say that there is at least one thing that is a bird that cannot fly. So we could say there exists an x such that x is a bird and x cannot fly. Now you can think of this as in 2 ways. You can say, oh, I have no specified domain, or you can say my domain is everything in the entire universe, and this still works. Now in colloquial English, this is a little bit ambiguous. Some birds can't fly. If we think that that just means a single bird, there exists a bird that can't fly, we've got much the same statement, much the same predicate wolf, I suppose, as we had before, right? There exists an X such that X is a bird and X can't fly. Now, it's possible that we wanted to talk about multiple birds that can't fly, and so we could talk about how there's at least two of them that can't fly, right? And we'll use that not equals trick again. So we could say, for example, there's two things. There exists at least one X and one Y, such that X is a bird and Y is a bird, and I'm going to start using a shortcut here. I'm going to say X does not equal Y instead of using a straightforward predicate. I'll just use this inline equals, just like we do for when we're programming. We use equals inline, or we use equals equals, right, or does not equals inline, instead of using a method. So what have we got here? We have, there's an X and a Y such that X is a bird, Y is a bird, X doesn't equal Y. All right, and we need to keep going. And X can't fly, and also Y can't fly. Okay, here's another example. All days are sunny. So it's the case that for everything in our world, if it's a day, it's sunny, right? So for all X, if X is a day, then X is sunny. Some days are not rainy. Let's take this colloquially to mean there's at least one day that is not rainy. So we want to say there exists an X such that X is a day and it's not rainy on X. Here's a little bit of a weird one. Every day that is not sunny is also not rainy. So this is talking about everything, right? For everything in our world, if it's a day and it's not sunny, then it is also not rainy, right? So for all X, if X is a day and, let's see, not sunny, then X is not rainy either. Let's shrink this a little so you can see all the parentheses. So I think we've got them right now. Let's see. So this thing, if this whole thing is true, that implies this little piece. And there's the outer ones. And so this X is covering all of that. Some days are sunny and rainy. So again, let's just use the colloquial some to mean there's at least one, right? So there is a day which is both sunny and rainy. There exists, why don't we do Q just for a change? There exists a Q such that Q is a day, and Q is sunny, and Q is rainy. No days are sunny and rainy. Now we've got there are no days, so there does not exist any, or for any day you pick, all the days are not sunny and rainy. So let's say there's no day, there does not exist a day. So it's not the case that there exists an X where X is a day and X is sunny and X is rainy. Now, so far I haven't actually talked about these constants over here. We can talk about constants just like we do in programming, and we can say things like, suppose M represents Monday and T represents Tuesday. If we want to say it rained both Monday and Tuesday, we're talking about two specific constant days now. We could say something like Monday was rainy and Tuesday was rainy. Or we could say something like Monday was sunny, so it was sunny on Monday. Therefore, every day will be sunny. So if it was sunny on Monday, that implies that for all X, sunny of X. Now notice that this is kind of interesting. because we sort of have some variables that are what we're going to call bound, right? This x here is referring to just kind of a variable x, right, where we said that's true for all x's. Whereas right here we have this constant Monday, so we're saying because it was sunny on Monday, and there's no existential quantifiers, no universal quantifiers, right? No for alls, no there exists. That implies that for all x, it will be sunny. And we'll talk more about this in a little bit. Now, the truth is we don't actually need to know the meaning to work with predicates. So your book says that for the most part they're going to use x, y, and z as variables. They're going to use a, b, and c as constants, and p, q, and r are going to be the letters representing predicates. So suppose I tell you here's a fact, all right, that p, which is some predicate of a, and p of b, and p of c, that these guys, that this wolf is a tautology, right? This is true. What can you conclude? This is kind of a weird question, but you'll see in a minute. What can you conclude if I tell you that my variables are going to be in the domain, which is the set containing a, b, and c, these three constants? And let me show you where I'm going here, and after this I think you'll get it. If you know that the predicate is true of a and of b and of c, and that my domain just involves a, b, and c, well, then I could say for all x, p of x, right? So everything in my domain, p of x is true because my domain is pretty small. I can also say there exists something in my domain for which p of x, because it's true for all of them, there's got to be true for at least one of them. So suppose I make the same statement that this predicate is true for a and b and c, but I change my domain. Now my domain is the letters a through f. What can I conclude now? I can't say it's true for all x anymore, right? Well, in fact, I can say there's at least one of them, right? And I can say it's not true for all of them. So here's another wolf that I want you to look at with some predicates and try and figure out what can we conclude. Now notice that I have changed it from and to or, so I know p of a or p of b or p of c, and I'm back to my original domain here. What can you conclude? Pause for a second and think. Well, since this is an or, we can conclude that one or more of these is true. So that's there exists an x, p of x. I don't know which one. It may be all three. It may just be one. Now, if you look at this one, I've really messed with it. I have p of a or, and then these two are anded together, p of b and p of c. So what can you conclude if I tell you x is in a, b, and c? Well, again, I'm kind of saying you can conclude that there's at least one, right? Because we know that either it's p of a or p of b and p of c. And there's probably more than just this you could conclude, but you can certainly conclude that there's at least one, right? I mean, we could go further and we could say, well, if p of b is true, then p of c is also true, or something like that. But just at its simplest level, that's what we can conclude. Okay, I seem to have changed my predicate now. The meaning of the predicate is something different because it now takes two parameters, right? Let's see, what do we got here? We know that p of a comma b and p of b comma b and p of c comma b. And if I tell you my alphabet is a, b, and c, can you think of anything that we could use the for all or there exists with respect to this p, this predicate? Well, how about this one? No matter what x you choose in the whole universe, right, which isn't very big, in my whole domain, this predicate is true for x and b, right? Because it's true for a and b, it's true for b and b, and it's true for c and b, right? So it's true for all of those things, anything in my domain. And of course, since it's true for anything in my domain, it's also true for at least one thing in my domain. Okay, so now that you have a feel for how these predicate logic Wolf's work, let's just look at the rules of precedence for a minute. Effectively, it's exactly the same as we use for propositional logic, except we add on the rule that if you have any quantifier or the negation symbol appearing next to each other, then, and what we say here is, and this is actually a quote from the book, the rightmost symbol is grouped with the smallest wolf to its right. So in practice, what does that mean? Well, if you look at this first one, actually let me move the rule down a bit so you can see it. So the rightmost symbol is grouped with the smallest wolf to its right, right? So here's the rightmost symbol in this first one. It's grouped with these guys, right? And then, so here we go. So this right one, this is with the parentheses, right, is grouped with that. And then we take the next one and group it with the stuff to its right. So this exists to y has the parentheses around that. The not connects to everything else, and the for all x connects to everything else. And I've made such a mess of that now that you can't really see it. So let's see if I can get rid of all those little red lines. There you go. Okay. Let's keep going and let's look at the second one here. So the second one is interesting because we have this exist x, right? It's going to go with the smallest wolf that it can to its right, which in this case is just this p of x, right? So if you look over here, these guys got grouped together. So it says there exists an x p of x or q of x. That's all one thing, or q of x. So notice that this x here isn't actually a part of this exists in x. We'll talk about more about that in a little bit. Let's look at this third one here. For all x, p of x implies q of x. Again, this for all is going to get the smallest thing it can next to it, which is just this p of x. So it looks a little bit weird when you parenthesize it, but that's what the rule says to do. If we look at this one, right, there's this exist in x, but this not is to the right of it. So this not is grouped with this predicate, and then the exist in x is with this big predicate, so we end up with the not with that first one, the exist with this whole thing, and then the implies is to something else entirely, right? And finally on this one, this exists wraps with the closest thing on the right, the for all wraps with the closest thing on the right, and you can see that happening over here. Hopefully most of the time you will just parenthesize stuff because it's such a pain when it's not put in parentheses. It's too easy to make a mistake. But this is a rule that's pretty straightforward. Okay, so you guys know about scope in terms of programming, and I've kind of referred to this in the lecture already without really being very, very specific about it. So now we'll talk about it carefully. So if you have an existential quantifier like there exists an xw, the scope of the existent x is w, right? So this x is kind of in scope in w, right? Scope of for all x in this is w, and so and so. In the absence of parentheses, the scope of a quantifier is the smallest wolf immediately to its right. Yeah, boring. Let's just keep going and look at this. It's often so much easier when you look at an example, right? So if we look at this first wolf here, I'll make it bigger, but not so big you can't see anything. This first wolf, we have this for all x, p of xy implies q of xy, and you know from the parenthesizing we did before that the for all x actually just goes with that piece, right? And so what's the scope of for all x? It's just that piece. On the other hand here, you can see I kind of parenthesized that whole thing, right? So what is the scope of the for all x here? It's that whole thing, and that's what the table says. The scope of the for all x is that whole thing. Getting a little bit nastier here, but let's take a look. Here's this for all x, and what's the scope of this for all x? Well, let's see. That parenthesis goes all the way to there. So the scope of the for all x is all the stuff inside. If we look at that same equation, but say what's the scope of the existential quantifier on y, the exists of y, right? We got to look and get our parentheses right here, but let's see. I think that one matches with that, and the exists of y goes around all that. So what's the scope of the exists of y? Well, the scope of the exists of y is this whole piece here, right? And I hope this is making sense. What's the scope of the for all z? Well, the for all z is just over that stuff, so same thing there. So we also talk about this concept of a bound variable versus a free variable. And we talked about this a little bit earlier. We kind of saw examples of this. So the question is, if I have an existent x or a for all x, is the variable within the scope of that quantifier, right? Again, we're going to look at some examples, and I think it'll become very clear once I show you a couple of examples. Oh, and just to mention, you know, your book talks a lot about bound and free variables. They briefly mention constants also, and we need to think about constants too, like when we were talking about M for Monday or T for Tuesday, those were kind of constants as opposed to variables, which may be free variables or bound variables. So here's my first example, and notice I say let x, y, and z be our variables and Kermit be a constant. Kermit as in Kermit the Frog, right? So suppose this is my wolf, right? And the question I'm asking here, well, there's no z, so I don't have to worry about that. The question I'm asking here is, tell me, is x a bound variable or a free variable? Is y a bound variable or a free variable? So let's look at this. We have for all x, and then the parentheses go like this, right? So all of this stuff, oops, is connected to the for all x, which means that this x and this x is bound to that universal quantifier, right? On the other hand, the y, there's nothing in here, right? There's no for all y, there's no there exists a y out there. So the y is going to be free. So here you can see a little bit more neatly, I actually wrote it out with some nice colorization. You can now say, wow, Dr. K, you obviously spent a lot of time on these slides, and just wait, they get better. But so as we said, x in this particular woof is bound everywhere, but y is free everywhere. Okay, here's another one. Looks almost the same, but if you look at the way the parentheses are, it's slightly different. So if you look at this, the universal quantifier here, the for all x, is around this guy, but not this one. So what does that mean? Well, y, again, there's not an all for all y, and there's not an exists a y. So y is going to be free still. Z doesn't even exist. But x is interesting because in this piece, x is bound, but in this piece, x is free. Right, and that's what I'm trying to say in this fancy graphic. Right here, x is in a rectangle, is bound. This particular x is free. So x in this whole woof is bound in some places and free in others. But the y continues to be free. It's not bound because there exists a y for all y anywhere in here that would bind any of these. All right, here's another one, and it's getting more complicated, so I tried to color code it. Let's see. If you look at this, and let's start with the z part, since that's kind of the innermost. This for all z covers this whole thing, right? The red bit here, and the only predicates that use z are inside of there, so that looks like that z will be bound. Meanwhile, the does not exist a y well, there's a y out here, right? And there's no y's in here. So that y is going to be free. And this for all x covers the whole thing here. So I guess x is going to be bound. And through the magic of instant slide fixing, you can see that that's what I've written here, right? So we got x is bound, y is indeed free, and z is bound. I think maybe I changed this on myself partway through. So here's the next one to look at. Let's take a look. Let's look from the inside out. If we look at the z, well, the only z's that exist are inside of these parentheses, so it looks like z is bound. The y here exists a y, covers this whole thing, and so now look at that, the y is bound. Yeah, I think maybe in this one I messed up there and changed this on the fly to do something interesting and didn't change my table. Anyway, I'm sure you're thrilled by that. Okay, and here the for all x, it covers everything, right? So that for all x, the x is going to be bound throughout here. So it looks like that. Let's try another. So notice here I've changed the parentheses a little bit, and in fact I've changed the letters a little bit too, right? So now if you look at the for all z, that still covers all the z's, so z is still bound. But for the exists a y, again we've got a case where it's bound here but free here, right? So it's both bound and free if you're talking about y. X, on the other hand, is bound everywhere. And that's indeed what I said here. And here's our last example. Now I've actually thrown a constant in here, right? So let's see. Z is bound, because that's the only z that's in there. Y, well, yeah, you know what? Now y is back to being bound. X is indeed bound, and Kermit's a constant. And so we have this to finish off our table. To wrap up this set of slides, I want to talk about something that we actually talked about pretty early on in terms of sometimes there's multiple ways to write the same predicate or the same woof using predicates, and that's because it's kind of always true. So in these examples that I'm going to show you, they always have a W, and that W, you know, could be any old woof that you want, right, that uses predicates. So it could be, you know, P of X, right, or P of X and Q of Y, and that whole thing implies, I don't know, S of Kermit or something, right? Basically, this is just any old woof that you happen to have, right? And this first predicate is telling me that if there exists somebody in my domain for which this woof is false, that's also saying it's not the case that this woof is true for everything, right? So if I say, you know, if my woof, you know, if in this case, suppose my woof is I of X, where I of X means likes ice cream, right? If I say it's not the case that everybody likes ice cream, that's equivalent to saying there exists somebody who doesn't like ice cream. And this equivalence is kind of the partner to that first one. If you say there's no value X, not at all, there does not exist an X such that this woof is true. Another way to say that is for all X, this woof is false. This one wasn't instantly obvious to me when I first saw it, but if you think about it for a minute, it makes sense. This says if for any X that you take in my domain and any Y, this woof is true, right? So pick an X and then pick a Y, this woof is true. Well, you know what? That's the same as saying pick a Y and then pick an X, this woof is true. Because remember, this is for all X, for all Y. Nobody's talking about, nobody says, oh, X has to be different from Y. They're both over the same domain. So if you have two for alls right next to each other, you can just swap them, swap the order, and it's still the same. Okay, let's do this next one again. Very, very similar to number 3. You know, if we say there's at least one x and there's at least one y where this is true, you can flip those around. You can say there exists a y for which there exists an x for which this is true, because of course nowhere have we said that x and y have to be different, have to be the same, nothing about that. It's just pick an x, pick a y, or pick a y and then pick an x. Okay, here a of x and b of x represent woofs with predicates in them, just like this w did before. So this is saying if you can say that there is some x for which if this a woof is true, that implies the b woof is true. That also says that for all x's where there is an a woof that is true, that implies there's some x for which the b woof is true, right? These two are kind of equivalent, well, no, exactly equivalent, genuinely equivalent, not kind of equivalent. I think this one's a little bit easier to understand. If I tell you there exists some x for which either this woof is true or this woof is true, another way to say that, I mean, this says there exists one x for which one of these woofs is true. This says there exists an x for which the first one's true, or there exists an x for which the second one is true. And last one, if you know for a fact that for all x, this stuff is true and this stuff is true, for every single x, both of these are true for x, then you can also say that's exactly equivalent to for all of them it's true for A, and for all of them it's true for B. Because of course if it's true for all of them for A and all of them for B, then it's also true for all of them for both. So that just about wraps up this set of slides. We have talked about an introduction to predicate logic, and talked about how to translate between English and predicate logic and vice versa. And we also did a little bit about these predicate, these predicate equivalencies, right? So what is it, how can you flip back and forth between different woofs in predicate logic? There are some things that are just always flippable, as it were, and that's what we did here.